Hello, everyone. I want to welcome you to our webinar series designed for CMI and by CMI. I'm Cynthia Howell, and I'm the Education, Training, and Outreach Manager for CMI. And I just want to tell you a little bit about the webinar. These are hosted by Colorado School of Mines, broadcast all over, from all over the nation at any given time. And about the webinar series, we're able to bring these great topics because people have recommended them. So please continue to add what you'd like to hear about and see about in this webinar. Also, this is a public webinar. A recording is going to be available next week at aimslab.gov, CMI, and it is now under the workforce menu, so please keep that in mind. Today, our presenter would like to have questions held to the end. We're going to be using the Q&A box like we normally do, but a reminder to you, it takes a while to type them in, so when you have your question, go ahead and cue it in so it'll be ready for the presenter at the end. I would like to introduce our presenter today. He is from Ocean Minerals, which is one of our new affiliates, and this is Hans Smit. He began his career in South Africa, an African Navy, and also then went into underground diamond mining off the southwestern coast of Africa. He is an experienced engineer and business project manager. And with that, he has worked in numerous underwater mining projects and has really worked on systems, instrumentation, software to improve productivity and systems. He has also, over the past decade, focused on deep water mining involving several companies and helping those companies with their engineering, operational, and management capabilities. He's a member of SME and of the International Marine Materials Society. But I don't want to take any more of Hans' time. I'd love to turn it over to him and take it away.
Thank you, Cynthia, and thanks for that great introduction. Yeah, thank you to the CMI for giving Ocean Minerals this opportunity to share a bit about our project. We're thrilled that we are now an affiliate of the Critical Materials Institute. And as we share a bit more about our project and you get a bit more visibility into what it is that we are trying to do, you'll be able to understand our enthusiasm for being a member of the CMI and how what we are doing and your objectives line up. Yeah, I'd like to hold questions to the end, as mentioned, predominantly just so that I can set the scene and give you a good overview of the project. And I'm not going to take up too much of your time presenting, so that we have a lot of time to engage and talk through the various questions that that folks may have. So. One of the things that we are all aware of is obviously the issue of critical metals. And these are critical insofar as they are essential to industry. They are key components of a lot of different components that the DoD and defense contractors are looking for, but also high-tech engineering and more recently the electric vehicle market. And what we're going to do today and during this presentation is focus predominantly on cobalt, copper, manganese, and nickel, with a bias towards the cobalt side, and then touch on rare earths as well. These are all key materials and metals, and I think everybody on the webinar is well attuned with with why these metals are essential. What we do know, however, is that these metals demand is going to be growing, and we also know that from a supply perspective, there are also a lot of pressures and sensitivities, and hopefully this project will show you how these can be addressed in the near term. Another factor from a geopolitical and social perspective, which also bears a lot of mentioning and consideration, is the sourcing, the refining, and the extraction of these metals. Two aspects from a U.S. and a strategic nationalistic perspective is that these metals are, particularly on the processing, that is the extraction and the separating side, these markets are dominated by China. On the mineral extraction side and the raw material side, their dominance isn't quite as big and quite as strong, but the issue we have with particularly cobalt is that there are very few sources of this material, and therefore you find concentrations and large parts of the current supply being focused in places like the DRC, Democratic Republic of Congo. From a strategic supply perspective, what is key about these metals is that for the US in particular, we have little or no raw material source of these materials. They are all imported, and we rely on imports from elsewhere, and that does create a lot of serious challenges, and particularly under the current political climate, it makes it even more challenging. On the socio-economic side, approximately 20% of the cobalt that comes out of DRC is mined by artisanal miners. These are kids and people, literally, as we see in the photograph, mining these chemicals, these metals by hand, and they are being exposed not only to terrible working conditions, but also there's a lot of secondary health issues that are associated with this. So this for us is an important consideration and an important factor that our project addresses head on, and particularly from a US perspective is key and important. And I'll talk about both the supply and the processing side as we move through the project. Now that we understand the demand and we know what the challenges and issues are, I'd like to shift focus to underwater mining and underwater resources. Our project specifically focuses on polymetallic nodules. As you can see in this photograph, polymetallic nodules are stones or rocks-like material that sit on the seafloor. The deposit we are looking at, they are probably, the average size is about the size of a ping pong, a little bit bigger, ping pong ball, and a little bit bigger, and they literally lay as a two-dimensional resource on the sea floor. As in the photograph, you just have this square kilometer after square kilometer of these nodules laying on the sea floor, and that is what we're after. And part of what attracts us to this deposit is the metal makeup, which I'll touch on, but the fact that it's a two-dimensional deposit and it just sits as a single layer, so it's not very complicated or very difficult to get to. Contrary to popular belief, people think or assume intuitively that this is an expensive resource to recover. The fact is that it's actually cost competitive and compares very well with current terrestrial mines. So, underwater mining is not expensive as one would think. And part of that reason is due to the concentration of the metals that we have in this ore body and the ease of being able to pick it up off the sea floor. What you're seeing here in the photograph is the apparatus we used in December of last year to go and do a sample and collect about 250 kilograms of these polymetallic nodules in order to bring them back to laboratories to do some testing with them. So how big is this deposit? It's massive. If you look at these graphs, if you look at cobalt, 16% of the current known cobalt deposits exist on land. That means the balance is in the ocean. The reason we highlight the Cook Islands here is because the Cook Islands is the area that we are specifically looking in, and I'll touch on that in a moment. But in the Cook Islands, 23% of the world's identified cobalt resources exist within the Cook Islands. But the big number is that 84% of the world's cobalt resides on the seafloor. And that would be either polymetallic nodules or seamounts and crusts. And the reason it's in those is because of the mechanism that creates the nodules. In crusts and nodules, the process is very similar. So that's why we have those concentrations. And similarly with nickel, we have a similar disproportionate amount of these metals in the ocean. And what makes these particular deposits incredibly attractive is, unlike on land where you have to drill, blast, dig, excavate, and spend a lot of money moving hundreds of tons of sterilized ore, with these nodules, they lay exposed on the seafloor and are easy to get to. And these numbers that we're quoting here are as a result of work done by the USGS. So, you know, this is this is just staggering information. When we first saw this, we were just confounded by the extent of this. As far as where we find these, they predominantly reside in the Pacific Ocean. And there are a couple of key areas where we have concentrations. One of the biggest areas that a lot of people know about is what we refer to as the Clarion-Clipperton Zone, or the CCZ. It's an area that lays between the islands of Hawaii and Los Angeles, in the middle of the Pacific. Very large area, lots of nodules. But there are challenges with this. This is all deposits that are within the International Seabed Authority waters, so they're in international waters, which means that they fall under the auspices of the United Nations. And from a regulatory perspective, there are challenges that are yet to be overcome. What we are looking at is nodules within the Cook Islands, and the reason we are looking at these nodules in the Cook Islands is an area down in the southern Pacific, in amongst the island chains. What you have is the Cook Islands, Fiji, Tonga, and so forth, in that sort of region. And that is where we are looking. The reason we're in the Cook Islands, two key fundamental reasons. The first one is these ore deposits exist within the exclusive economic zone of the Cook Islands, which means that we have to deal with the Cook Islands, and it's within the control of the Cook Islands government. More importantly, in 2009, the Cook Islands published underwater mining legislation, legislation that is specifically written for underwater mining projects. So we have a clear, well-structured framework of how to apply for licenses, how to get exclusive rights. And for us, that's very important, that we have exclusive rights and we have protection of our rights right through to what is necessary to get a mining license and beyond. So we have a great legal framework within which to work, and it is very clear and concise as to what it is that we need to do. As far as our company itself is concerned, under these Seabed Mineral Act, we have entered into two agreements with the Cook Islands, and these agreements give us exclusive rights to apply for exploration licenses over a number of areas. And what we have here, if you look at the graphic on the right, is we have blocks numbered 1 through 5. Blocks 1 through 5 are reserved for sediments, and the sediments that we are interested in contain high concentrations of rare earths. And in block 4 and 5, we have an additional agreement that in addition to the sediments, we also have exclusive rights to the polymetallic nodules. And the polymetallic nodules is what we are targeting for cobalt primarily, and nickel and manganese as secondary byproducts. The area that we're looking at, block 4 and 5 combined, are roughly 20 to 24,000 square kilometers. And within that area is where we have our resource. As far as our resource is concerned, in the mining world, you have two standards, or two bodies that provide guidance with regards to defining and reporting a mineral resource. The one is the NI 43101 technical code that is under the auspices of the National Instruments, the Canadian Institute. The other one is JORC, which is the Australian equivalent. And what's important about these is it standardizes reporting of resources, so that you know, there've been some really bad instances where investors have been fleeced by unscrupulous parties, and this goes to addressing that issue. So using that, those guidelines, what we did is, with the available data we had back in 2018, we compiled a report. And the size of the resource that complies with the reporting requirements is what we have captured here. So we have 203 million tons of nodules over roughly 9,500 square kilometers. But what's staggering here is that we have 1 million tons of contained cobalt. We have 500,000 tons, give or take, of contained nickel, and 31 million tons of manganese. But a copper and the iron is something we're not interested in. But what is important about this is that this is primary cobalt. And the reason that is a key differentiator is currently cobalt is mined as predominantly as a byproduct. So it is a byproduct of nickel mining or byproduct of copper mining. So to address the imbalance with regards to cobalt supply that we're anticipating in 2023 through 2025, we would need either cobalt or nickel mining to increase their volume. That's not going to happen because, well, it may happen with nickel, but it's certainly not going to happen with copper because the copper market will not be able to absorb the large amount of additional copper that is mined in order to get the corresponding cobalt. So this being a primarily cobalt deposit means that we can go and target cobalt and bring as much cobalt to the market as required by the market, and we can ramp up and scale up as needed without having to worry about byproduct impacts. That being said, when we do get more cobalt, we do bring more nickel to the market. There's a big nickel market and there's deficits there as well, so we don't have too much of an issue there. On the manganese side, that's a market that we're going to have to be a little more circumspect about, but we are targeting manganese for the EV market, so the battery market. So we expect that there will be a corresponding market to sell that into as well. The other interesting part about these nodules that in addition to these four metals, we also have rare earths, and the rare earths we have is a reasonable spread, and we do have a couple of the rare earths that everybody's looking for. So we do have neodymium, we do have praseodymium, and a couple of the others that our folks are looking for. It's not huge amounts, but it's certainly interesting amounts. The graphic on the bottom right gives you an estimated tonnage of material of each of these groups that we can bring to the market as part of our ongoing production facility. So work we are currently doing is actually quantifying how much of this available tonnage will be able to be brought to the market. And I'll touch a bit about that when we get into our processing slide in a moment. So the other key thing about this resource is that if you look at it in forms of in scale and magnitude, the Democratic Republic of Congo currently produces 65% of the world's cobalt demand, and they have the world's largest mines in Kamato, Katanga, Mutada, and Funagurume. Now, what is important about our resource is that as far as our reported resource size is concerned, we are somewhere between the known cobalt deposits on land versus what we know about in the Congo. So we find ourselves in the middle of the two. But we also know, based on work that we've done, that there's a lot more polymetallic nodules in our area that we haven't been able to report because we don't have enough data, referred to as an exploration target under the JORC code. We estimate we have a total of about 2.5 million tons of cobalt, which puts us in line with the largest DRC mines, which means that this project of ours has the ability to come on stream and to directly and unequivocally address the shortage of cobalt that has been predicted in 22, 23 and beyond. I think the other important thing to note is that all the known deposits that exist on land, which are represented by the blue dots on this graphic, show that they are all under 500,000 tons of cobalt, and a lot of them are even smaller than that, which means that they're not significant deposits. It means that you need to have a lot of these to be able to make up the shortfall that is being projected. And the other challenge that we have is that the price of cobalt for these mines to make an economic case has to be in the region of $60,000 per ton, in order for the economics to work. So there are a lot of challenges trying to bring these mines on board, bring them on stream. these are issues that our project addresses head on and gives us an opportunity to move this forward. As far as the economics are concerned, because we have a high concentration of cobalt, we have 0.5% cobalt in these nodules. It means that we get a lot of cobalt for a lot less raw material that is being moved. So that is through the byproducts and through the grade. That is how we are able to increase the revenue per ton of ore that we're moving, and that's why we are able to compete with the land-based mines. So how do we get it up off the sea floor? It's actually very simple, oddly enough. You literally just drag a vacuum cleaner over the sea floor and you lift the nodules up and you bring them up to the surface. We have in our proposed mining system, we have what we refer to as the collector. It's the machine that we drag across the sea floor. It has a bunch of suction nozzles, much like a vacuum cleaner, across the front. And what it does is it lifts up the top 2 or 3 inches of the seafloor. So it will pick up the nodules and a couple of, an inch or 2 of the sediment underneath it. But then on the machine itself, we separate the nodules from the sediment and we discharge the sediment out the back of the machine immediately back onto the seafloor and leave it behind. We do it for 2 reasons. One is by doing that, we minimize the amount of environmental impact in the form of pluming and disturbance. Also, we don't have any mechanical pumping action. It is all done through induction and induction flow. So any critters or micro fauna biota that are in the seafloor are able to pass through without having the risk of being chopped up by any mechanical impeller or mechanical device. So we deposit the sediment out the back in order to mitigate from an environmental perspective. And then we also don't want to pump the sediment all the way up to the vessel, because that consumes power, and power is our single biggest cost, is power generation. So what we do is we concentrate the nodules on the machine, and then we use the pipeline that comes from the machine all the way up to the surface to suck the nodules from the machine and bring them up to the top. And we do that by injecting air into our vertical riser pipeline at about 4,000 feet. What this does is it creates movement in the water column, and that in turn creates a suction. When we get this up to the surface, we separate the ore from the water, we return the water back to the sea floor, and the nodules don't need any beneficiation. They are literally temporarily stored in a hold, discharged into a bulk carrier, and sent ashore for processing. Now, what's interesting about this concept is that it was proven and done back in the 70s. So we have the various consortia back in the 70s that proved all of this technology. And then we also have the diamond mining industry that has been operational in Namibia and South Africa for the last 35 years, using the same technology. So the technology is there, the technology exists, and it's proven. It's just a question of adapting it for this particular environment and operation. So now we have the nodules ashore. Now we have to extract and get the metals out. This is where we've been doing quite a bit of work. During the 70s, Dr. Jay Agrawal and his team, who were at Kennecott, developed the Cuprian process. But that process was specifically targeting the Clarion-Clipperton Zone nodules. What we definitively know is that the nodules in the Clarion-Clipperton Zone and the nodules in the Cook Islands are different. The nodules up in the Clarion-Clipperton Zone are nickel dominant. The ones in the Cook Islands are cobalt dominant. So there's a chemical difference between them. So what we've done is we've taken the Cuprian process and we've modified it. And what we have been doing over the last 6 months, and why we went out at the end of 2019 to go and collect nodules, was to be able to run these tests. And we have, over the last, since January, been running tests. And this is a modified Cuprian process using a sulfate extraction process, and it's leaching. So it's a sulfate leach process. And what we are, the reason we went for this is a number of things. One is it's low temperature. So we don't have the issues with all the high temperatures that some of the other processes, the pyro processes and the HPAL processes are using. And also it's at atmospheric pressure, so we don't have to have pressure vessels. So this has been really encouraging for us, and what we've, the initial results we got back so far are indicating that we are able to run the process at 30 degrees Celsius is the optimal temperature. So we're really going to save as far as energy consumption is concerned. And what we are reporting is that we are getting 90% better cobalt extraction. We're getting about 70% copper, 85 to 90% nickel, and about 60 to 65% of the manganese is reporting through this process. What we've also been able to identify is that all the rare earths that are contained in these nodules are pretty much ending up in the leaching residues. So our next phase of testing is to have a look at this leaching residue and look if we can separate out the rare earths and make an economic case for that separation. So this process has been ongoing. We've been proving it up. So we have confidence that we can extract the metals, get them into solution. We're busy precipitating out the metals and looking at what options we have as far as final products, sellable products are concerned. But we definitely have a case for getting them out. What we did do during this month was in response to the critical metals FOA that was published. We submitted a white paper, and what we want to do is take this process of ours that is probably at TRL level 4 and do the work and pilot it and take it up to a TRL level 6 or 7 status. So we're hoping that we'll get positive consideration from the relevant authorities. So, this is our next big task as far as the processing is concerned. Environmental is a big issue with regards to mining. Irrespective of where you are in the world, environmental issues are environmental and community are key drivers. Anybody who ignores that is going to be in trouble. So what we have at OML is a very thorough, proven mechanism of dealing with the environmental side of things. There's been a lot of work done, contrary to what the NGOs are publishing all the time. There's a lot of work that has been done in the ocean with regards to studying the environment in which we work in, mitigating the impacts, and we have mechanisms called adaptive management and the precautionary approach are two mechanisms that we use extensively. And what that means, the precautionary approach is the fact that we do not have all the data does not mean we cannot proceed. What we have to do is proceed with caution, but we have to have a feedback loop where anything that we learn gets brought back into the process and we reassess and adapt on an ongoing basis. And that's where the adaptive management principle comes into the fold. So this is a feedback loop that works all the time, and as we learn more, we grow. The other thing that we also transition to is ecosystem-based modeling. And what this is all about is if you can model the ecosystem and you can understand what the interdependencies are of the different components, what you can now do is establish key monitoring points that are early indicators of a disruption to the existing ecosystem. And by monitoring them real time, you are able to immediately pick up where there's an impact occurring, and you can take an intervening action before you end up with a catastrophic scenario, or worst case where you end up with some loss of life, be it animal, biota, or human for that matter, because this process is applied across the board. So this is a well understood, well engineered process that is being used by the whole underwater mining industry, and we in the industry we share the processes and what we are doing. And we involve the scientific communities, we involve the NGOs, we involve the contractors and the end users, because at the end of the day, what's the point of developing a green economy and a green green power consumption if the mechanism of acquiring the raw materials and producing the product to develop it is flawed. It needs to be green from the beginning through to the end. So this is an important part of that. The caveat is we need metals, and metals, irrespective of where you get them, has impact. What we need to do is make sure that the impact is minimal and acceptable. As far as specifics that we've been doing, what we engaged with from a community perspective is we developed a software package called Pelagos. It's a pelagic observation system. And what's key about this is that one of the issues we want to address is that when campaigns like this happen, or when companies get involved in underwater mining, because of the cost of marine expeditions, you tend to do them infrequently. And what happens is, if you're only collecting data that is supposed to be baselining an ecosystem, and you're only collecting it once or twice a year, you are missing a lot of the seasonal variability that does occur and is important to capture. And through developing Pelagos, what we've done is created a tool that we can put in the hands of the community in the Cook Islands, and have the community go out and help us characterize and define what the environment is. And what's great about this is it doesn't only help us from the mining side to baseline what's going on in the Cook Islands, it also helps the Cook Islands national environmental services, the cetacean communities, and the other communities looking at bird life and coral reefs and so forth, allows them to go and collect data and build up their own databases of information that can be used. So this is a great tool that we've rolled out that is being used and is now being adopted more widely in order to do this process. So, you know, it's important that we pay back to the communities and have them involved, because you know, this has to be to the benefit of all. Economics, you know, it's important that you know, this is all good stuff and we can get it, and we have all these metals, and you know, we have this one ore body that is producing anywhere between 4 and 8 of the metals on the critical materials list that has been published here in the US and in Europe, but it doesn't make any sense if it doesn't make money. You know, what we don't want to do is subsidize an operation like this. So what for us has been very important is through the development of this project is not only deal with those strategic and critical metal issues, so that these markets can survive and develop and support the green evolution that for us is a key driver. We need to make sure that the economics work. And what we've done is through the fact that we have multiple metals, it's a real polymetallic ore body, together with innovation in how we design and build our mining system. And our mining system does look different to what the other guys are doing, and how we are looking at processing, which is also different to what everybody else is doing. The whole focus has been on driving down the cost per pound to produce these various metals. And this graphic is of particular importance because what it shows is OML's current projected financial model is showing that we compete with the large mass producers of these materials as they currently exist. This cost curve here is the projected. The blue is the existing copper and nickel processors that are producing cobalt. The gray, the blue's copper, the gray is nickel, and these towards the end are the companies that are you know, much smaller and more costly, and to the left is where the big mines are. And you can see that OML sits down at around the 40 percentile region of the cost curve. And this is before we have done any optimizations with regards to our process and improved things. So our starting point is a very low cost per pound or cost per ton to produce these metals. And we believe as we go forward, we'll be able to improve these even further. So it's not this expensive, prohibitive mechanism for getting materials. It's actually quite the opposite. And then finally, before I just introduce our team, the timeline. You know, how long do we see this happening? We expect that the initial process is driven by the environmental permitting need. We have to have an environmental permit to proceed, and we have to baseline the environment in which we're operating. So for the next 3 years, we are going to be collecting huge amounts of environmental data, and we're going to be baselining the environment in which we work in. And we are then going to do an impact assessment with regards to our mining method and our operations, and generate a environmental impact statement in about 3 years' time. Once we've done that, we can then apply for our mining license, and we can go ahead with our mining license. Now, in order to collect that data, we've planned for 5 expeditions out into the Cook Islands to go and collect this data. Each of these expeditions occurs during a different time of the year, so that collectively the data collected over these 5 campaigns will give us a good indication of seasonal variability. And while this is all ongoing, we will continue working in parallel to develop our mining system and to develop our processing system. Next year is earmarked for doing the pilot testing of our extraction process. And then we also want to work with companies to get into separation, and we also want to work with end users so that we can make sure what we're producing at the end of the day is ready for the market. And one of the interesting things we're talking about at the moment is we're working with one of the end users and actually looking at modifying our process that we produce at the end of our processing phase, the ready mix product that they need to go straight into cathode manufacturing, rather than the separate entities that they have to remix and then combine for their use. So we are again being innovative and taking this upper level, and that's key to our entire project. It's all about innovation. It's all about improving the technology. It's about bang for the buck. We want to be efficient, effective, and we want to maximize the ability to optimize technology. And if that means developing new technology, then so be it. We will definitely do that. So that gives you a great overview of the project, what it's about. It's very high level. There's a lot more detail. But finally, I just want to introduce the team. We have a great team as part of our group. Dr. John Halkett is the founder and chairman. Interesting about John is he was one of the original members of the consortia that did this work. He was part of the Kennecott consortia back in the 70s and was the lead engineer for the Kennecott underwater mining program. So, this is, his career coming full circle. It was his first real job, and now that is, in retirement, he's back here doing this again. Myself, I've spent the last 20, 30 years in underwater mining off the west coast of Africa, and more recently in the deep water side of things. I really have a passion for this. David Huber, deep sea drilling, he was part of the companies that were involved in a couple of the key early deep sea deep water drilling expeditions. So, you look at the 3 of us, there's an extraordinary engineering and deep water capability there. Jack Lifton, people in the critical metals industry know Jack. He's been around. He's a stalwart of particularly on the rare earth side. And then Carl Winter, also in the deep water oil and gas side. So a lot of experience with this kind of application. And then the executive management team, the other guys that come in here are, Laurie Meyer has got 30 years experience in the marine and aerospace engineering. So, brings a lot of that, those procedures and the structure and the management to the team, as well as a solid engineering analytical mind. Dr. Colin Seaborn, metallurgist, but a metallurgist with a financial background. So whenever he's working on our processing side, we are looking at the economics while doing the process. It's not just pure science, it's about economic science. And that's a key thread throughout our whole team. Adrian Flynn, Dr. Adrian Flynn on the environmental side. Adrian has spent the last 20 years, working in the ocean, and his speciality is deep water and shallow water, marine and ecological systems, and he's well respected in the industry, is well thought of, and has a proven track record in the deep water industry. So we have a great team. And then Duncan on the capital markets, financing is a key and important part. And these are just the management team. In support of us, we have a lot of associates and advisory board members that all have experience in this field. So we have a formidable team that can certainly pull this off and make this happen. So that's the overview. I hope you found it interesting, and I'll welcome and gladly answer any and all questions. Thank you.
Hans, I'd like to thank you for such an exceptional presentation on this ocean mining lab and the project work that you've been engaged in with your entire team, your thorough overview with the supply and processing side issues, environmental issues, economic opportunities and issues. Really remarkable, all the way to the end of engaging the Cook Island citizens in being citizen scientists and helping you collect data. So a very thorough project, and certainly important to CMI. So I do see that we have a few questions, and I wanted to ask you if you would not mind reading out for the archiving process, if you wouldn't mind reading out the name, and then also the question so that it can be archived for future reference. So looks like your first question is queued in.
So this is Emilio Castello. Thank you, Hans. 3 questions. What might be the main challenges for deposits outside the EEZs? Should we better focus on deposits inside the EEZs? Emilio, for us, we believe that the EEZ at the moment is absolutely the place to be. The reason for it is specifically due to geopolitical and regulatory risk. When you're in the EEZ, like we are in the Cook Islands, we deal with the Cook Islands government, we deal with the Cook Islands as a nation, and we deal with the Cook Islands population. So we have a definitive group of people that we can engage with and we can interact with. And that makes the process of being able to move the project forward obviously a lot easier. They also have well-defined legal frameworks in place, and even other countries, in other companies that I've worked with, for example, in South Africa, where we have the underwater diamond mining industry, and you go to places like Papua New Guinea, Solomon Islands, Tonga, where they may not have the underwater mining legislation and as advanced as the Cook Islands are. What they do is they use their existing terrestrial mining legislation and apply it to the ocean. So for us, that's why we're there, and we believe that makes a lot of sense from a business perspective, because you have this framework and this and you have people that you can deal with, and invariably they also have goals that are similarly aligned to where we are. These are Pacific Island nations. They are looking to diversify their reliance on service industries. The Cook Islands, for example, the largest part of their GDP is as a result of tourism, and followed way behind that would be fishing, and to a certain extent, and not as much anymore, is financial services. So what happens is with COVID, for example, the Cook Islands are in trouble because 65% of their GDP is reliant on the tourist industry. With this underwater mining opportunity, it allows them to diversify that, and it also allows them to have a product that is not, or a source of revenue that is not as reliant on those, those key issues, be it a cyclone that comes through or a dengue fever outbreak, etc. So that's why we focus there. There are a lot of companies and countries focused in the forward, but the challenge they have, and the challenge they have been having for the past number of years, is the lack of regulatory framework. So in answer to the question, that's the reason we're there, and that's why we would advise anybody to stay in the EEZs. Okay, Bruce Moyer, CMI funds tiara level TRL 2 to 4 research, what are the technical advances that would make your chemical extraction and refining more efficient? Or do you believe that the issues are all primarily scale up to TR5 and higher? Bruce, no, there are, you know, there are areas within that TR level 2 to 4 that we still need to address. At the moment, we are predominantly focused on the extraction part of getting the metals out and moving them forward. But certainly on the separation side, that is where, you know, there's still a lot of research to be done, and particularly making sure that we can find separation mechanisms that or methods that are economic. You know, this is a new, unique ore body. These are the first time that tests of this scale are being done on this ore body. It's never been done before. Up until our cruise in December, we'd been relying on parallels that we've, you know, through deduction as to what they've done in the Clarion-Clipperton zone. So yes, there is a lot to be done there, and there is great opportunity. I think what needs to happen is we need to sit down and engage with folks that are in that you know, extraction and separation field, and get our team together with them and look at, you know, where are the you know, where are the areas that we can look at and find that we can spend some funds on and use that in a meaningful manner to develop a process for doing that. Charlie Fuller, has consideration been given to processing in situ to reduce power consumption? Charlie, yeah, good question. One that we've spent a lot of time looking at. I think the big challenge we have is that this is a leaching process. So in order to be able to look at doing this in situ would require a fairly sizable platform because of the volumetric area that you need for leaching tanks and so forth. So that's one challenge that is the issue. The other challenge is that this is not a stable platform. So you have something that is in motion all the time. And with the leaching process, you have liquids, and large surface area of moving liquid on a vessel at sea is a very serious safety hazard because it creates instability on the mining vessel. So that's another challenge that we have with regards to that. And then the final one is a lot of the chemicals that we use. You know, now you have to start looking at what happens if you have a spill or you have a catastrophic failure of a tank, and all of this material, because you don't really have the ability to effectively create cofferdams, etc. What happens if you have a spill? And then the last worst case scenario is you have a vessel that gets irreparably damaged and sinks in sight. What would the environmental impact of that look like? So the key drivers of why we don't do it at sea are attached to those particular areas. What we are looking at from a power consumption perspective is how can we use alternate power sources in order to reduce our carbon footprint and also to make the power generation less complicated. And I think the final comment on that is we have two large consumers of power, and the consumers of power are one, the station keeping of the mining vessel, and the reason that is a big power consumer is we cannot use anchors. The water is too deep. We're in, and I don't think I mentioned that in the presentation, the water depth where we're operating is 15,000 feet. So having anchors is impractical. And secondly, the vessel has to move all the time because it's the vessel's motion that drags the collector across the sea floor. So we use a lot of power just station keeping and moving the vessel. And the other thing we use power for is to pump the material up to the surface. Trying to beneficiate it on the sea floor, that just creates engineering challenges and introduces risk that when you start looking at it from a risk perspective is prohibitive. All right, Yoshiko Fujita, you mentioned that the metal-rich crust deposits and polymetallic nodules are believed to have been formed through the same mechanism. What is the current thinking on what that mechanism is? They are similar. They are both created through accretion. So it is, either, the metals coming up through the sediment and accreting to some form of starter material and forming a nodule, or water, or the materials depositing and accreting out of the water column onto the nodule. So that is where they are similar. And we have also found in areas where nodules have joined together and have created crust-like areas. So it's that process that gives us the two. Now, what we do found with crusts is they tend to be on higher hill-like areas. The nodules tend to be in the abyssal plains, but there's a similarity between the two. But if you'd like more information specifically to that, you can just drop me an email and I will get our geologist to engage with you and give you very detailed specifics to that. Alex King, what is the deepest seabed resource that has been commercially covered so far, and how does its depth compare with the Cook Island resource? Yeah, great question. The commercially recovered, implying that it's made economic sense and is producing money, would be the diamond mining industry off the coast of Africa, where the water depth is about 600 feet, 700 feet, in comparison to 15,000 feet, where we are in the Cook Islands. That is the key dissimilarity between the two projects. There are a lot of key similarities between the projects. The vessels operating in Africa are nearly as remote as they are in the Cook Islands. In fact, it actually takes us longer to get to the African deposits from our support base than what it does in the Cook Islands. The Cook Islands are slightly closer. So the water depth is the big key driver. Now, as far as the rest of the operation is concerned, there's a lot of similarities. The logistics, the production, the support facilities. A lot of the equipment is very similar as well. The difference between them would be the depth. But the depth is only a real challenge when you have enclosed housings, and there are well understood and well known mechanisms to address that. So yes, it is a step change from the current economic commercial mining, which is the diamond mining, to the depths that we're at. But what we do know is that it is doable. In the 70s, they recovered about 1,500 tons of nodules using these mechanisms. So we know it's doable. It's just a question of getting it on a continuous basis. But that's where the history and the knowledge that we have from the Namibian and the South African diamond mining comes into play, because we have 30 years of underwater mining production knowledge and experience that we can tap into. Charlie Fuller, is the extraction typically done using operators or robotic systems? Charlie, the answer is all the machines are remotely controlled. There are no humans going down onto the seafloor, but there is human control. So, we have operators that man the operation rooms all the time. We have people that are monitoring the equipment. The equipment is largely automated, but there is operator supervision at all times. And that is to make sure that we have eyes on the system all the time. When things start going wrong, you don't want to have people that are not readily available to make the necessary interventions and to ensure that the system doesn't go down. This is a production environment. The objective is to be engaged and harvesting all the time. And if you are not harvesting, there has to be a damn fine reason why you're not doing it. Philippe Sanchez, what would be the major risk that you see for the project to move forward, the different phases of the Plan Master Program? I think, Philippe, for me, the largest risk is funding. This is a new sector, new industry. It is difficult for people to evaluate and for them to really get to grips with what is the risk profile associated with this project. What does it really look like? it's human nature that if you have no frame of reference to compare to, that you assume the risk is high, and that's what we have. So for us, the key fundamental challenge at the moment is funding, and having funding to take the project from where it is now to a point where it is mature enough that traditional project financing can kick in. So that would be the key risk. The next risk, I believe, would be around the environmental side. And the reason I say that is not because I don't believe we can deal with the environmental side. It's because the environmental issue is an emotional issue. And you know, it's about making sure that as an organization that we engage with the local community, the populace, the scientific community, and as many of the NGOs as possible, and have them part and parcel of this development process, and satisfy everybody that we are in fact doing it in an environmentally friendly manner. In doing it that way, we can satisfy ourselves and everybody else that this project is not going to have any impact. On the technical side, I think, you know, we don't have huge risks. What we have is some technical challenges to overcome. And then probably the last one is the risk that every mining project has, and that's commodity price. You know, at the current prices, we have a project that is slightly better than break even. We need the prices to go up a bit. But I think that's the case with most mining projects, is you know, you're in production, but you always have one eye on the markets and looking where the prices are. Eric Clear, what is the interest worldwide in deep ocean mining of nodules, crust, etc.? Eric, I think the interest in nodules is where everybody's real attention and focus is, mainly because it's intuitively it's doable, and intuitively you can see that there's a mechanism to do it. And then of course the fact that it has all these metals is really attractive. Crusts creates more of a challenge. The crusts require a more traditional mining mechanism where you actually have to excavate, cut, or grind. So you're looking at a very different machine that has to go in there and grind up the crust and then recover it. So from a technology perspective, it is more challenging. From an environmental side, it's also, also going to create a lot more headaches. And then finally, with the crust, the crust is this, you know, fairly thin layer of material that is crusted over either rock or a substrate. And with grinding, it's not very selective, so you end up getting a lot of sterilized overburden coming up with your mined ore products. So it starts affecting the economics. And then Heather Merlitz, what gives you confidence that 5 trips over 3 years will provide sufficient ecosystem data to prevent irreversible environmental damage? How do you envision the Cook Islands community engaging with this new industry? And how do you feel the economics and timeline compared to asteroid mining? All right. So with regards to the 5 trips over 3 years, those are the 5 major trips, Heather. So those are the trips that we have to bring in specialized scientific equipment in order to address a couple of key issues. And they will occur at those instances. What we have done in addition to that is using local vessels and the local community. We have a series of additional trips in between these that are planned. And then together with tools like the Pelagos system, as well as benthic landers, which we are developing, we are also going to have additional mechanisms that will do additional sampling in between. The final thing is that we have a number of long-term arrays that we put into the water columns. So there are these full water column as well as partial water column moored arrays that we put in, and they actually remain in situ for the entire 3-year period and beyond. And we go back on a regular basis and collect that data. And that would be collecting data such as water currents, temperatures, We also have hydrophones on them so that we can detect any animals and cetaceans. We have water samplers on them. We have nephlometers, CTDs. So there's an array of instruments on them. So we actually build up a fairly comprehensive seasonal picture. The questions disappeared, so let me see if I can.
Hans,
Yeah,
you may go back to that final question. It's in the answered column, but
yeah.
I also want to take a moment. The broadcast is going to be ending here soon. Again, to thank you for a great presentation. Thanks everybody for attending. And again, we would like to have everybody back again with us on August 19th for American Manganese Incorporated. It's going to present advanced lithium-ion battery material recycling. And of course, you can always find that in the critical times. All right, Hans, if you want to continue on with that question, we are good for about one more minute.
All right, thanks, Cynthia. The Cook Islands community, how we're involving them is that we are using their facilities. We are using the infrastructure that exists within the Cook Islands. We are also have training programs and developmental programs that what we are doing is our operations are going to be based in the Cook Islands, and they're going to be largely manned by Cook Islanders. In addition to that, as the project develops, there'll be an industry that comes into being on the Cook Islands in order to support this. So we are looking at not only on the scientific side, labs and environmental, we are also looking on the practical side from electrical, mechanical, hydraulic, IT, etc. So that is where the islands over the long term are going to benefit in the form of increasing job markets, increasing opportunities. But in the near term, every time we go out on a cruise, we take Cook Islanders with us and we make them an integral part of our team. When we were at sea in December, we were actually outnumbered 2-1 by the Cook Islanders as part of the team going out there. So they are a key, important component of our mission. And then finally, economic timeline to asteroid mining, we're going to beat them hands down. We're going to be bringing up these metals 2026, 2027. We'll start producing these metals. I think asteroid mining is going to take a little longer than that. So I certainly think that we're going to beat them in that regard. As far as the economics are concerned, I don't know what the economics for asteroid mining look like, but I would think that if you're paying tens of millions of dollars to launch a rocket, and you look at the cost to develop the equipment, I would think that we stand a better than even chance of being able to beat them on the economic side as well. But yeah, I'd like to have that debate with somebody over a beer and get into more detail. But my feeling is we can beat them on both economics and timeline.
And on that positive note, Hans, I want to thank you again for a great, engaging presentation. And I look forward to seeing everybody again on August 19th. Thank you.
Thank you very much.